Inverters have assumed a fundamental role due to the dramatic growing of electric machines and especially of all technologies related with renewable energies. But what is an inverter and what is it for? In electronics, the inverter is an electronic input-output device that can convert direct current as input into alternating current as output and change its amplitude and frequency parameters. As we've already explained in our previous video on the history and operation of the electric motor, the common electrical socket in our homes provides us with alternating current. It is generally used to power large electrical devices such as home appliances, etc. If we look at the alternating current, we will see a wave pattern in which the voltage alternates between its two maximum and minimum symmetrical peaks, passing through a zero value. The alternating current can be compared to sea level between its extreme conditions of high and low tide. Among these extreme levels, seawater will flow at intermediate levels, also changing direction. The common batteries, on the other hand, provide continuous current and represent a typical example of direct current voltage generators. Their characteristic is a fixed polarity at the terminals, called positive and negative poles. This type of current is mainly used by devices such as electronic boards and is also generated by solar panels. The continuous current is always theoretically at the same voltage and its current always goes in the same direction, as a time function can be represented by a straight line. For analogy, we can imagine a river or channel that flows continuously in a straight line in one direction with a constant flow. Inverters are often used in solar or photovoltaic panels. These devices, in fact, always generate direct current, while, as we have said, the appliances in our homes use alternating current. To operate the appliances, therefore, a conversion from direct current to alternating current is required. This is why there are various types of inverters on the market. JAES, in its catalog, offers a wide selection of inverters from the major manufacturers. A more complex type of inverter is necessary when it is integrated into a frequency converter or into a control unit to manage and control the speed, torque, and direction of AC motors. As we saw in our previous video on the sizing of centrifugal pumps, a practical way to change the rotation speed of the pump impeller is to use a frequency converter to maintain unaltered the other design parameters. It is common to find inverters used for the control of pumps, fans, compressors, and in basically any rotating equipment. As we see in this animation, the inverter is coupled to a rectifier, so the alternating current is converted into direct current, and then again into alternating current. The interesting part is that the internal drivers will change the frequency and consequentially the shape of the sine wave. This configuration precisely controls the performance of a motor connected to a mechanical load such as a compressor, etc. In this video, we will explain how to obtain an electric current output with a pure sinusoidal wave from a continuous direct current. Alternating current periodically and symmetrically reverses its direction. For this reason, the average value of the alternating current on a cycle is 0. Before proceeding with the construction of the sine wave, we see what a square wave looks like. In this 3D, we can see the reconstruction of a circuit with 4 switches and an electrical supply. This circuit is known as a diode bridge inverter. The output is represented between points A and B. In this case, the input is represented by a common battery, and this is the hypothetical load. As we can see, there is a current only if the switches C1 and C3 are connected and C2 and C4 are disconnected. Now it's enough to invert dually the switches and observe the current flow direction. It is easy to observe in this case the current is in the opposite direction. Also, the voltage through the load changes its value from positive to negative. Basically, this is the technique that produces an alternating square wave from direct current supply. In our homes, the current is alternating at the frequency of 60 Hz. which means we would need to turn on and off the switch 120 times in a second, something impossible to do manually, even using mechanical switches. For this reason, semiconductor switches come into play. MOSFET transistors are capable of switching on and off thousands of times per second using control signals. These signals can easily adjust the switching on and off of the transistors. The shape of the square wave represents the first approximation of the sine wave. The old inverters that produce square waves are easily recognizable by their classic buzz during their operation, like fans or other devices that use square wave powers, also because usually their internal components get very hot. Modern inverters produce a pure sine wave output. Let's see in detail how they do it. The technique is called PWM, from pulse width modulation. The purpose of pulse width modulation is simple. A square pulse of variable time length and variable voltage amplitude is generated so as to compose a shape very similar to a sinusoid. This is now the most complicated part. What happens if we mediate these impulses in a tiny amount of time? You will be surprised to see that the average pulse shape seems very similar to the sine curve. The thinner the pulses used, the better the sinusoidal shape will be. In this situation, how can we produce these impulses, and how do we find a practical way to obtain an average? Now, let's see how these pulses are implemented in an inverter. For this purpose, we use the comparators. Comparators compare a sine wave with triangular waves. One comparator uses the sine wave, and the other comparator uses an inverted sine wave. The first comparator triggers the switches C1 and C2, while the second comparator triggers the switches C3 and C4. The switches C1 and C2 determine the voltage level at point A, and the other two switches determine the voltage level at point B. So you can see that the output branch of the comparator is equipped with exclusive logic. It means that when C1 is open, C2 will be closed and vice versa. We can never turn on C1 and C2 simultaneously because this will cause the DC circuit to short circuit. If we turn C1 on, which gives cell voltage at point A, and if we turn C2 on, we'll obtain a voltage equal to 0. Same thing for point B. The switching logic of the pulse width modulation is simple. When the value of the sine wave is higher than that of the triangular wave, the comparator produces a trigger signal, otherwise the signal is 0. Now, let's look at the voltage variation. The control signal of 1 turns on the MOSFET. The voltage pulses produced at point A are shown. Just apply the same switching logic and observe the voltage pulses generated in point B. Since we are tracing the output voltage between point A and B, the net voltage will be obtained from the difference between A and B. This is the pulse train that we need to create to approximately obtain a sine wave. A smaller and more accurate triangular wave is as the pulse train is. The question rising now is, how do we implement the media in a practical way to make it exactly sinusoidal alternating electric power? Passive, reactive elements, such as inductors and capacitors, are widely used to smooth the power waveform. These elements combined in circuits are called passive filters. The inductors act on the current while the capacitors act on the voltage, and it is the combination of these passive components that make up the so-called filters, make the wave trend more gradual, and reduce the typical scaling of pulse width modulation conversions. The inverter technology that we have now explained has only 2 voltage levels, but what happens if we use an additional voltage level? This will give a better approximation of the sine wave and will lead to a reduction of the instantaneous error. This multi-level inverter technology is used in high-precision technologies such as wind turbines and electric cars. The inverters used in electric cars have adjustable frequency and amplitude. in order to regulate vehicle speed and power. In fact, control through a complex logic of voltage and frequency changes the speed and power used by the car as a central brain that optimizes the parameters for an ideal guide. Finally, if you found this video useful, let us know by leaving a comment and subscribing to our YouTube channel to stay tuned on the latest release of new videos. Thanks for watching.